Hello students, myself Amrita Dhar, Assistant Professor of Electrical Engineering Department of Greater Kolkata College of Engineering and Management, JIS Group.
In this video, I will discuss about quadrilateral speed time curve and tractive effort during acceleration, tractive effort on a gradient, tractive effort for resistance. This topic is included in module 1 of the subject utilization of electric power and subject code is EE-702. In the previous video, I have discussed about trapezoidal speed curve. In this video, I will discuss about quadrilateral speed curve. So first, I draw the quadrilateral curve. So this is my speed axis and this is my time axis. Okay. This is point O, this is A, this is B and this is C. So this is the quadrilateral speed time curve. Sorry. Speed time curve. Okay. I draw a perpendicular on OC axis from point B and A. Suppose this is point D and this is point E. This is velocity v1 and this is the velocity v2. This angle is tan inverse alpha and this angle is tan inverse beta c. And this angle is tan inverse beta. This is time t1. This is time t2 and this is time t3. So total distance D is equals to area OABC. So total distance is equal to this area under OABC, and this is equals to OAE plus AEB plus EBC. OAB, OAE, AEB and EBC. That means this area and this area. So this is the total area. And AEB is equals to DEB. Okay. this is equals to OE and this is equals to DBC. Now this is equals to half V1 T minus T2 by 3600 plus half V2 T minus T1 by 3600, which is equals to 1 by 7200 T V1 plus V2 minus V1 T3 plus V2 T1, and this is equals to T V1 plus V2 minus, and T3 is equals to V2 by beta, and T1 is equals to V1 by alpha. So if I take common V1, V2, then it is become 1 by beta plus 1 by alpha, or 1 by alpha plus 1 by beta. Okay. Now V2 is equals to V1 minus beta C T2, V1 minus beta C T minus T1 minus T3, and T1 is equals to V1 by alpha, and T3 is equals to V2 by beta. What is alpha and what is beta? I have already discussed in the previous video. Alpha is the acceleration and beta is the retardation in kilometer per hour per second. So V2 minus beta C by beta V2 is equals to V1 minus beta C T minus V1 by alpha, and from here and from this we can write V2 is equal to V1 minus beta C T plus beta C by alpha V1, 1 minus beta C by beta. Now from these equations we get value of D, V1 and V2. Next, average speed and schedule speed. Average speed and schedule speed. So what is average speed? Average speed is equals to distance between the stops by actual time of run. And schedule speed, what is schedule speed? Distance between the stops by actual time of run plus stop time. Okay, average speed is equal to distance between the stops by actual time of run, and scheduled speed is equal to distance between stops by actual time of run plus stop time. Now factors affecting scheduled speed are value of alpha, value of beta, maximum speed and duration of stop. Okay. So this affected by alpha acceleration, beta deceleration, Vm maximum speed and distance and duration of stop. Now for a given distance between the station, greater the value of acceleration and retardation, less will be the actual time of run and more the scheduled speed. Similarly, for a given distance between stops and fixed value of acceleration and retardation, greater the value of maximum speed, less will be the time of run and more the scheduled speed. Now average speed remains same, increase in duration of stop decreases the scheduled speed. Now station stoppage time has been much effect on the scheduled speed in case of urban and suburban areas services where running time itself is very small because the distance between two stations is very less. When the distance between the station is much, the duration of actual time run time is also long. Station stop has less conspicuous effect on the schedule time. Next is the tractive effort. Next topic is the tractive effort. Now tractive effort is the force developed by the traction unit at the wheel rims for moving the traction unit and its train. Now drawbar pull is the force exerted by the traction unit through the drawbar for moving the train, and thus drawbar pull is less than the tractive effort by the force required to move the traction unit. And tractive effort exerted by the traction unit has to perform some functions. First, to give a necessary linear and angular acceleration. To the train mass. Second, to overcome the gravity. Gravity component of the weight of the train. To overcome the wind and frictional resistance. To overcome the wind and frictional resistance. To overcome curve resistance. Now tractive effort, now we derive the expression of tractive effort for acceleration. Tractive effort for acceleration. Now force is required to give linear acceleration to the train is given by Fa is equals to 1000 W into alpha into 1000 by 3600, that is 277.8 W into alpha, unit is newtons. Now when the speed of the train is being changed, it behaves as a mass greater than its dead weight, and this is due to angular speed variation of its rotating part. Now if linear acceleration is f meter per second square and angular acceleration of rotating parts having radius of gyration r meters will be f by r radians per second square. Now if I is the moment of inertia of rotating masses and if the force in newtons applied at the rim of the wheel, the torque applied, that is F into R, where F is the force and R is the radius, given by F into R equals to I into F by R. Now this is equals to, now F is equals to I F by R square. Now suppose this is equation 1 and this is equation 2. Now magnitude of force as per equation 2 will be in addition to the force required to give linear acceleration, and equivalent additional mass of rotating masses is I by R square. This additional mass is best expressed as a percentage of dead weight of the train value, of which lies between 8 to 15%. Now we will now introduce the concept of effective weight of the train WE, which takes into account not only the motion of the translation of train but also motion of rotation of wheel axles and armature of motors and gears. Now equation 1 becomes Now this equation becomes 277.8 into WE into alpha. This is equals to 277.8 by 9.81 WE into alpha, WE into alpha kg. Now we convert the Newton to kilogram. So we divide this equation by 9.81. Now tractive effort to give acceleration of 1 km per hour per second to 1 ton is given by FA is equals to 28.3 into 1.1 into W into 1. Okay. Now we assume WE is equals to 1.1 W, that is equal to 31.1 W kg. Now tractive effort by train weight, tractive effort by train weight is equals to 31.1 by 1000 into 100, that is equals to 3.11%. Now from, suppose this is equation 3, now from equation 3 it is observed that tractive effort required to give an acceleration of 1 km per hour per second is 3.11% of the weight of the train, which is equivalent to 5% for an acceleration of 1 meter per hour. Now usually values of acceleration adopted for different services are, for goods it is between 0.21 to 0.29 kilometer per hour per second. For parcel it is lies between 0.35 to 0.53 km per hour per second. For passenger train, it is 0.53 to 1.08 km per hour per second. For suburban, it is between 1.08 to 2.16 km per hour per second, and for metropolitan service, it is between 2.16 to 3.16 km per hour per second. Now, tractive effort required to balance the gravitational pull. Required to balance the gravitational pull. Now, when the train is on an up gradient, gravity component of dead weight of train parallel to the track W sin theta will be responsible for the train to come down. Now, in order to prevent this, tractive effort has to be applied in upwards direction, whose magnitude is given by Fg equals to 1000 W sin theta into 9.81 newtons. Okay, now in railway practice, gradient is expressed as the rise in meters in a track distance of 1000 meter and is denoted by letter capital G. So, capital G percentage. So, capital G is equals to sin theta. Now, I draw a diagram. So I draw a diagram. It will help to understand better. This is equation 1 and this is equation 2. Now, from 1 and 2 we get Fg is equals to 1000 into W into G by 1000 into 9.81. We just put the value of sin theta, that is G by 1000. So, this is equals to 9.81 W into G, unit is Newton, or W into G, unit is kg. Now, location of the gradient has important effect on the overloading that can be permitted on the traction motors. For instance, if short pulling ruling gradient happens to be after a ground down gradient, it does not create any problem as momentum of the train takes it up the steep gradient. On the other hand, if ruling gradient happens to be in the middle of a rising gradient, the length of the gradient becomes very important in determining the temperature rise of the motor. Another factor which affects the overloading of motor is the location of signal with respect to gradient, and if stopping signal is the foot of a rising gradient, speed pickup will be low and motors are likely to be overloaded. Now, our next topic is tractive effort to overcome train resistance. Now, train resistance consists of all the forces which oppose the motion of the train on level track. Now, these forces can be classified as those forces which are internal to the rolling stock, such as friction at journals, axle guides, bogie pivots, buffers, etc., and those forces which are external to the rolling stock, such as friction between wheels and rails, flanges friction resistance as a result of temporary deflection of the track and aerodynamic drag, and flange friction increases the oscillation of the coach and is affected by the side wind pressure, and track resistance depends upon the strength of the track and nature of the ballast, and aerodynamic drag consists of pressure drag and frictional drag, and former may be due to the ends of the later due to pressure drag and fractional drag, and former may be due to ends and later due to the length of the train, and end resistance comprises head resistance and tail resistance, and due to suction of air at the rear, both of the end resistance depend upon the area perpendicular to motion and the shape of the front and rear end and wind velocity. Now, since head resistance is about 10 times the suction resistance shape of the front carriage is very important in reducing the wind resistance, and wind resistance due to the length of the train is due to air friction on sides and due to underside of the train, and this is sometimes termed as skin friction. The pressure drag is found to be far less the frictional drag for long trains. It is found that endeavor to diminish the pressure drag is not so effective for reduction of total drag, and aerodynamic drag of Tokaido line was determined by F is equals to 0.20 plus 0.0045 L into P by 2 A V square kg. Now, what is L? L is the length of the train in meter. A is the cross sectional area in meter square. P is the air density. In kg per second square per meter to the power 4. V is the speed of the train and unit is meter per second. Now, all the internal and external resistance excluding wind resistance are termed as mechanical resistance. Apart from wind resistance, all resistance are termed as mechanical resistance. And although different components of mechanical resistance behave in a different way with increase in speed, it is reasonably correct assumption to consider mechanical resistance as a whole to remain constant, especially at high speeds, and is proportional to the weight of the train. Now, wind resistance on the other hand is considered to vary with the square of the speed of the train, and total train resistance in case of electric train is given by Fr equals to A plus B into V plus C into V square. Now, V is the train speed and A is the constant representing the mechanical resistance. Like journal friction, track resistance, etc. B, this covers the several factors like flange resistance and internal friction. And C covers the air resistance. Now, however, total resistance is given by Fr is equals to 9.81 R into W Newton or R into W kg. Now W is the weight of the train including locomotive and R is the train resistance in kg per ton. Friction or starting friction. Now starting friction, which is called friction, is more than the running friction, and this very much depends upon the starting condition of the train. For example, starting resistance of the train will be more if inter-vehicle couplers are in tension, which happens in case of up gradient. On the other hand, inter-vehicle couplers will be in compression and starting resistance will be low for train standing on down gradient. And it is due to reason that signal should be as far as possible not be placed up on gradients. Even on level tracks, it is a better practice to move back locomotive by few meters so as to release inter-vehicle tension. And this makes the starting friction low, as it is observed that starting resistance is due to first few vehicles. Once train starts moving, resistance drops and remaining of the vehicle are easily halted by locomotive. Now formula adopted by SNCF is for gradient up to 7% are gradient per 1000 plus 4.5 kg plus 4.5 kg up to 10 ton axle load, or gradient per 1000 plus 4.2 kg above 10 ton axle load. Now for gradient above 7%, the R is equal to 1.25 gradient per 1000 plus 2.75 kg up to 10 ton axle load, and 1.25 into gradient per 1000 into 2.45 kg above 10 ton axle load. Next is the tractive effort to overcome kerf resistance. Now kerf resistance is due to the friction at wheel flange, and more the radius of the curvature, less will be the kerf resistance. Kerf resistance is given by FC is equals to 700 by R W kg, where R is the radius of curvature in meter, and in railway practice sharpness of the curve is expressed more conveniently in degrees of curvature than by radius of curvature. 1 degree curve is defined as that which in 100 foot or 100 by 3.27 meters turn through 1 by 3/60 of a complete circle, or in a track of 100 meters it turns through 3.27 degree curvature will have 5730 by 3.27 c meters as a radius of curvature. Substituting this for value of R, we get FC is equals to 700 by into 3.27 by 5 0.30 C into W kg, which is equal to 0.4 C into W kg. Now curve resistance is usually taken to be part of train resistance and is combined with the total tractive effort. In that case is given by Ft is equals to Fa plus Fg plus Fr plus Fc. Now which is equals to 28.3 We into alpha plus minus Wg plus Wr plus 0.4 C kg, or 277.8 into W into alpha plus minus 9.81 Wg plus 9.81 Wr plus 0.4 C. Sometimes in traction mechanics, it is convenient to express curve resistance is equivalent gradient resistance and is given by equivalent gradient per thousand is equals to 0.4 C. Now expression for total tractive power now becomes Ft is equals to 28.3 We into alpha plus 0.4 C plus minus G into W plus W into R kg, unit is kg, or 277.8 We into alpha plus 9.81 0.4 C plus minus G W plus minus 9.81 W. Positive sign is to be taken for train movement up gradient and negative sign for train movement down gradient. In the next video, I will discuss about tractive effort speed characteristics.
That's all from today's class. If you have any problem, please contact with me. My contact details is given on the first slide. Thank you.